Quanta Company has created Aspen flowsheet simulation for the hydrogen hydrate and the nitric acid. The Haber-Bosch stage starts with the nitrogen and the hydrogen feed streams as the reactants. The stream is then compressed to 100 bar and warmed to 450 Celsius degree in B101. Inside the reactor, the nitrogen and the hydrogen react to form ammonia with 20% conversion. The mixture is then condensed in a flash drum so the ammonia becomes liquid while the unreacted gases rise and are recycled and purged. The liquid ammonia is then removed to the on-shown plan and divided into two equal parts. One continues to the Oswald stage to make nitric acid, and the other continues to the PCUK stage to make hydrogen hydrate. The total production of ammonia is around 2.5 times 10 to the power of 4 tons per year. Moving on to the Oswald stage, it begins with ammonia and enriched air as the reactants. This enters the first reactor. Here, the ammonia combusts with oxygen to form nitric oxide and water. The mixture is separated in a flash drum so that most of the water leaves from the base and the gas rises. This gas then joins more enriched air and passes through a cooler and a compressor before entering the next reactor. In this vessel, nitric oxide reacts with oxygen to form nitrogen dioxide. The nitrogen dioxide then enters an absorption column where it reacts with water which is fed from the top alongside the water separated. The nitrogen dioxide and the water react to form nitric acid and a small amount of nitric oxide. The mixture is cooled and separated in another flash drum as the liquid product while the gas is purged and recycled for reuse. The products nitric acid with 5.59 times 10 to the power of 4 tons per year and 82% purity by weight.
Let's now move on to the PCUK process to make hydrogen hydrate. The feed consists of ammonia from the Haber-Bosch stage, hydrogen peroxide, methyl-ethyl ketone, and the catalyst acetamide. The stream is mixed, compressed to 3 bar, heated to 75 degrees Celsius before entering the first reactor. This mixture settles into 2 layers, which is then separated with a liquid-liquid separator. The water and acetamide are removed from the bottom, while MEK and MEKazine are removed from the top. It is then purged and recycled for reuse. The clean MEKazine is then joined with the water stream from the earlier distillation column. This mixture enters a second reactor at about 175 degrees Celsius and 100 bar. This MEK then gets recycled and purged. So the hydrogen hydrate moves to a final distillation column, where more water is removed from the top, and the result is purified hydrogen hydrate, which is removed from the bottom. With these feed flow rates, we make hydrogen hydrate at around 46,600 tons per year, at 71% weight purity. Here's our final Aspen flowsheet.
We'll now look at our simulation decisions for our Aspen flowsheet. For our thermodynamic properties, RKSBM was used for the Haber-Bosch section, because the equation of state methods give reliable thermodynamic predictions at the very high temperatures and pressures found in the ammonia production. More common methods like NRTL were not suitable here, because it's designed for liquid phase behavior in non-ideal mixtures, while the Haber-Bosch process operates mainly in the gas phase, when equation of state is far more accurate. For the PCUK process, we decided to use NRTL for base method because it is designed for non-ideal liquid mixtures, where the behavior of each component depends strongly on the local surroundings, which the model captures through its local liquid structure approach rather than assuming random mixing. This makes it well suited to the PCUK process, as it can represent uneven molecular interactions found in water-rich and highly polar mixtures, giving stable and realistic liquid phase predictions throughout the simulation. For the Ostwald process, we decided to use ELEC NRTL, as it is more tailored to handle systems with electrolytes, which are present in the process. For example, the Ostwald process is responsible for producing nitric acid, which is a strong acid, meaning ion dissociation is present. For our processes, we use R-Stoichiometric reactors because the reaction pathways and the conversions had already been researched and fixed in advance, while R-Equilibrium and R-Gibbs were not suitable since they would instead calculate the new equilibrium outcomes or minimize energy based on all possible products. For the areas where separation is required, Flash 2 was used when there was a clear gap in volatility between the materials being separated, such as water and nitric oxide. Flash 3 was not used because it's intended for systems that form 2 separate liquid phases. SEP was used to model the flash separation of the ammonia feed because it allows direct control of the composition in each outlet, avoiding the issues caused when small amounts of gases such as argon, oxygen, and hydrogen disrupted DSTWU calculations. SEP was also used to represent the liquid-liquid split between the MEK and MEKazine, which is suitable when only the distribution of components matters. The decanter was not used because it relies on the detailed liquid-liquid equilibrium data, and the Aspen databank does not provide the accurate phase behavior of the mixtures such as MEKazine and water, thereby saving computation time, while SEP2 offers unnecessary features like purity specifications. The SEP block efficiently achieves the necessary mathematical split. For our selection of distillation columns, DSTWU was chosen for 3 of the 4 distillation columns, because it offers a quick and reliable shortcut method for early design when the detailed behavior of the column is not essential. Distill was used instead for separating hydrazine hydrate and water because DSTW could not handle the azeotrope that forms between these two materials, meaning it could not reach the purity needed for the final product. Distill was selected to model the final hydrazine hydrate and water separation because it forms full equilibrium calculation and can handle mixtures that do not behave ideally, including azeotropes. This allowed the model to achieve realistic representation of the limited separation possible between the hydrazine and water.
In our base case simulation, energy demand is dominated by heaters and coolers, accounting for 46.5% of the total heat duty, hence this will be our main focus. The objective of the heat integration study is to quantify baseline utility use and then apply pinch analysis to determine the thermodynamic minimum. Bosch and PCUK Oswald are integrated separately due to geographical constraints, while the distillation columns and the reactors are also excluded to avoid any thermodynamic interdependencies. The three exchanges below also exhibit phase change throughout their respective temperature range, hence they are also being excluded. For the Haber-Bosch, the pinch analysis predicts 90.8% recoverable sensible heat, while Aspen achieves 87.5%. This close value shows that this loop performs thermodynamically well for heat recovery. The minor differences are maybe due to limited heat transfer area. Next, Pinch estimates 60.6% recovery for PCUK Oswald system, but Aspen only achieves 27.9%. This difference is expected, given that the pinch constant heat capacity flow rates and no phase change penalty.
So we used Aspen to identify the sensible temperature range, which is not including the phase change, so we used this sensible range for a pinch method. And this is the interval diagram for Haber-Bosch. And this is the cascade heat diagram. From this diagram, we can see that the pinch point is below the interval 3, and we need hot utility. And this is heat exchanger network diagram that shows our design from pinch analysis, PCUK and Oswald. And these are the found sensible temperature ranges from Aspen, and we use this range for our pinch analysis. And this is our interval diagram, and with this interval, we drew the cascade heat diagram. From this diagram, we can know that we don't need heating utility for this case, so the pinch point is the top of the interval. Also, from the composite graph, we can check the pinch point again. For onshore process, we need 4 heat exchangers and 3 cooler for remainders of hot stream.
The all-around status for the Aspen flow sheet was very good, with only one error message appearing during simulation. This message simplifies stated that Aspen had loaded correct binary interaction data from the ENRTL IG bank data, confirming that the property method had been set up properly for the electrotype calculation. When looking at the convergence behavior, the PCUK section reached a satisfactory tolerance after about 250 iterations and settled very close to 0, while the Elsterwald section needed around 110 iterations to stabilize. The Haber-Bosch section converged almost immediately, showing that its part of the flowsheet was straightforward for the solver. Thank you for listening. That's all about our presentation.